Hey everyone, just a little video here on Cartesian, cylindrical, and spherical coordinates in Desmos, and just some things you can do with those types of surfaces and whatnot. So I have a few points that are up here. One is Cartesian, one is cylindrical, one is spherical, and we'll kind of move these around in a minute and see how those go. So we're going to start with the Cartesian. These, I assume, are familiar to you. Typical X, Y, Z types of things. I have some sliders in for A, B, and C. And we can see that these guys will move. With the A is going to move in the X direction, right? So the X varies. The B is going to move in the Y direction, so that the Y varies. The others hold constant, and then the Z, right? The C will move in the Z direction for those guys. So that's kind of how that one is set up. Now, one thing to keep in mind, I'm going to put in a few extra things here, is that a lot of times we're thinking of basically three types of movement, right? So there's the X, Y, Z direction, and if you move in two of these but hold the other one constant, you kind of form this plane. So if I move in the X and Y direction but hold the Z constant, then we get this peak plane that is perpendicular, I should say parallel to the XY plane. If we get movement in the other two, then we get something perpendicular to the XY plane. So if we hold our Y constant and just move in the X and Z, then we're going to get kind of this dark bluish one here that's perpendicular to the XY plane but parallel to the XZ. And then this light blue one, this is if I hold the X constant and then just move in the Y and Z direction. So if I just move the B and the C, then I can move in those two directions, but nothing changes on that light blue plane. X holds constant. So that's kind of how things will move. We're going to compare some similar stuff with cylindrical and spherical coordinates in just a minute. But that's kind of the basic movements of Cartesian. So I'm going to go ahead and hide those for just a little bit. So I'm going to take those off. Now if we check out the cylindrical, and let me go ahead and hide the spherical. So this is going to be the purple one. The cylindrical points are going to be given by R, theta, and Z. And R and theta you can think of as your typical polar coordinates. So R will tell you how far to go out kind of in this XY plane. Theta is going to tell you how much to rotate around this positive x-axis around here. And then Z will tell you how far to go up. So if I go ahead and move some of those. So the R, right, is going to kind of move things in and out, right, away from that Z-axis. That is what the R is going to do. The T, right, this is the theta is going to spin things around, right, so things spin around the Z-axis with that one. And then the C, right, this is going to move things just kind of straight up and down, right, so straight up and down with those. Again, it might not be obvious just looking at it kind of plain there, but if I go ahead and put in some of these fixed planes, then this is what we have. So this light blue, again, is going to be where R is fixed, and I'm just moving in the Z and theta direction. So if I move the C value, right, that kind of moves things up and down, but that light blue one stays fixed. If I move the T, right, that moves this one around, but again, light blue is fixed. So R is fixed in that. And this is kind of where the name comes from, cylindrical coordinates, because we hold our R constant in this coordinate system, then we get the shape of a cylinder. So it's kind of named for that. If I hold my T constant, right, then that's this this orangish looking plane right here. And if I hold my C or Z constant, right, that is going to be this pink one. So you'll notice the pink one here looks very similar to Cartesian. That's because it is just the XY movement. Instead of X and Y's, I have R's and T's, right? This R and theta that I'm going to use for these guys. So that's what we get for these. But these are kind of the degrees of freedom that I have to move. If I change my R, I change the radius of that cylinder. So that kind of moves in on those. But if I don't change my theta or my z, then both these orange and pink planes are going to stay fixed. And so R will just change that one parameter right there, which moves things in and out along this line of intersection between the theta and the z. Spherical are going to be somewhat similar to cylindrical in that I'm going to have an r and a theta. So you'll see a very similar r theta kind of circle and this rotating plane that goes around. But this time, instead of a circle, let me go ahead and hide these guys. We're going to get a sphere. And again, it might not be obvious until I put those planes, or I guess they're not planes anymore, but those surfaces in there. This r, right, is going to basically be now, instead of just distance from the z-axis, this is going to be distance to the origin. So this origin point 0, 0, 0, that is going to be the distance, right, that we go out there. And this is what we usually call rho. So spherical coordinates will usually have something called rho. In fact, if you want, I'll go ahead and type in kind of that coordinate. If you type RHO, it kind of looks like a little script P there, but that is the Greek letter rho. And then theta, right, and this time instead of Z, we are going to get this Greek letter, which is phi. So PHI with the Greek letter phi, and again, Desmos will replace it with that symbol that's right there. So rho, theta, and phi are what I'm looking at. As rho changes, right, again, I go a distance from that origin point out, whatever direction I'm pointing in. The theta will again kind of rotate me around that z-axis, whichever way I want to go. And then the phi is going to change the angle between the z-axis and this place that I'm pointing at for that point. So that phi changes the angle between the z-axis and this vector that's pointing toward this coordinate right here. So as I go to 0, right, we'll kind of go to that upper z-axis. And then as I go down to pi over 2, we're in the xy plane. And then down to pi, down to the negative z-axis. So that is what phi is going to do. Now if I try to look at my coordinate surfaces, right, where I hold one of these constant and move the other two, that is going to look something like this, right? So we have kind of this rho, right, instead of r. So we have rho is this sphere. And again, this is where the coordinate system gets its name. Spherical coordinates are because that rho is just going to change that sphere from different radii to different places that are along there. So that's what that's going to do. The theta, right, is going to do just like what it did before. So it's going to rotate around to different places, kind of in the XY plane, but then also just going vertically right up, just rotates around that z-axis. And then the phi is going to widen this cone that's right here. So if you want to see that cone more, you might have to zoom out, but that is going to be a cone that widens, kind of flattens once I get to this pi over 2, right? So then I'm kind of right there in the XY plane, sort of the usual coordinates that I would normally get. But then as phi continues on toward pi, right, I start getting that cone shape again. So this would be my constant phi, is whatever angle that is between the z-axis and the cone. That's what I'm getting for that guy right there. So as you hold things constant, right, one of these will change, the other two will not. Or if I want to change two of them, keep the other one constant, right? If I want to keep that phi constant, I can expect my point to just kind of rotate around along the surface of that cone. And as I change my r, or instead of r, we're doing rho. For this one, as I change my rho, we're just going to be able to move up and down that cone. So this will go up to the point of the cone. This will go down toward the end of the cone. So that's what is going on with those guys. Converting between all these coordinates, right? These are all sharing the same 3D space. So if I were to show all of these, it would look like a big mess, but they all are sharing the same 3D space. So a lot of times what we want to do on these is go ahead and try to convert from one to the other. A lot of times that is for either simplicity of graphing surfaces or for integration type purposes, either making the bounds nicer or the function nicer to integrate. And so that's one thing that you will expect to do is just kind of convert coordinates one to the other to start, and then later on convert surfaces. I'm going to go ahead and hide a couple of these guys real quick, and I'm going to go back to this Cartesian one, show that point right there in Cartesian coordinates. Again, this is kind of the A's, B's, and C's. You can look at if you want to change those right to any point you can. And then I'm going to show this vector basis right here. So this is kind of the thing that we're looking at for converting from R's, rho's, thetas, phi's, x, y, z's, all of that is kind of these lines right here. And I'll show you a different picture as well in a second. But that phi is going to form the angle between this upper z-axis and that vector that's going along toward my point. And then this purple and red are both the r distance, right? So we can say this rho is going to be, if I want to think of it as r, right? This is my r, that purple one, and phi is the angle down here, right? So phi is going to be opposite of this r. So we got rho is going to be this r, or I should say, let's do it this way. The sine, right? Sine of this phi is going to be the r over the rho. And I can also convert that to r is rho sine phi. So this purple and red distance right here, that is our r, and that'll be rho sine phi. Likewise, the z, which is going up, right? This is adjacent to this phi that's right here between the greens. So that is going to be the cosine of phi, right, is going to give us the z over the rho, or I could say z is rho sine phi. So that's kind of that upper triangle. Down at the bottom, you have your usual x, y, r that you'll get. So x is our cosine theta, y is our sine theta. That's exactly the same thing you had in polar coordinates, but that can sometimes help looking at this, converting between the rhos and the phis and all of that. So last thing we'll kind of take a look at is these overlapping coordinate systems and some of the formulas that you can get out of it. So like I said, if it helps, you can draw some of these like x, y, theta, phi, rho, r's, all kind of in the same place, or separately if it helps to view them separately. But these are the conversion equations that you should get, is right here at the top. So x is our cosine theta, y is our sine theta. Again, that's just from our 2D system that we normally had. That 2D system kind of lives still in this xy plane, right? So I got the x, y, r. That doesn't look like a right angle with the perspective put in, but that is a right angle right there in the bottom left. And then we also have the r squared as x squared plus y squared. Rho squared, because that lives on a sphere, that is going to be x squared plus y squared plus z squared. So that is our rho squared equation that we can use. And then z, like I said before, is going to be rho cosine phi, r rho sine phi. These last two you kind of get for free. Just take your r cosine theta for x, replace the r with that rho sine phi, and the y, that is r sine theta, replace that r with rho sine phi. And you'll get these last two equations for x and y in terms of rho, phi, and theta. So that's kind of it for conversions. So when you're going through conversions, there'll be a separate video on going through those. But these are the formulas that you're going to want to have handy to be able to use. The last thing I'll say is in Desmos, you can plot surfaces as well. So I'm going to go ahead and hide these guys again. And we'll just plot a few surfaces, right? So if I'm plotting some surfaces, I can put them in my typical, right, x, z is like x squared, right, plus y type of format to get whatever kind of surface I'm looking at. And we can even put in like a sine y, something like that, and view the surface that comes out, right? So that is just put in your usually z equals, but it doesn't have to be. Desmos will handle a lot of times other stuff like x squared plus sine y plus cosine z, right, equals 1, and then it'll show you what that surface is going to look like. So it'll do implicit surfaces as well. It'll also do the cylindrical and spherical as long as you use the correct names. So if I want to use z is r sine theta, then it'll plot that right sphere. Here it's saying, what do you want your r to run between? What do you want your theta to run between? And right now it's doing theta from 0 to 2 pi. It's kind of the default. R is going 0 to 5. So we get kind of this slanted disk that's right here, slanted circle, where the z is going to be kind of that top end at 5. If I want to make that a bigger, maybe like 10, we'll get a bigger circle on that, but that's kind of what it's looking at right now. And you can put in, right, whatever you want. If you want this to be r squared, right, or something else, maybe I'm going to do cosine of r, right, the parentheses around that, and then cosine of phi, right, then it'll try to plot in whatever weird, right, looking surface is going to be met with that equation that's right there. Again, subject to those parameters, right? If you want r to go out to infinity, you might put in just a big, like 100 or 1,000, right, for the r. Theta is typically going to be 0 to 2 pi for that type of stuff. You could also do this in spherical coordinates, right? So this time we're going to do a row, again, RHO, we'll give you a row. And this one we'll say we're going to do theta and phi. So let's do cosine theta and then sine phi. And then I'm going to put in maybe like a 9, right? So this is a sphere, right, of radius 3. It's not centered at the origin, right? It's kind of over here. And so you might think, huh, well, why is that? Well, if you go back and convert to some of your other coordinate systems, then you might see, oh, yeah, that's kind of the shifted sphere equation if I convert back to x, y's, and z's or things like that. So you can, again, this is going to be subject to theta 0 to 2 pi, phi 0 to pi. That's pretty typical ranges for those. So usually you're not going to have to mess with those unless you only want a slice of what's going on. Then you can change it. Right? If I only want theta to go 0 to pi, right, give me kind of, well, in this case, that's still most of the surface there. Let me say maybe pi over 2. Right, then I'm only getting, right, half of a surface, right? So I lose that part where the y is negative in that case. And so if you want to change any of those parameters, you can sometimes see, like, oh, which part is actually graphing what part of the surface by making some restrictions on those guys. So any equation you want to type in, rows, cosines, phis, it does sometimes have a little bit of a hard time. Let's see, plus row equals 9. So if I put in something like that, right, then it's going to say too many variables. I don't really know. It doesn't always do implicit stuff like this, like it does with some of the other equations. So you might have to put things in terms of row, right? So I might say minus 9 equals row. Still not sure if I put row equals in front. Let's see. not PHO, RHO. Now it knows right what to do. So it's a little more picky on the spherical coordinates, whereas the rectangular, right, or Cartesian coordinates, those it's going to be able to do all kinds of stuff. So I'm going to make this go back to 2 pi, just so we can see that. So again, that's that sphere again. This time, not quite a sphere. It's got kind of this dimpled piece in here, so almost like a 3D. If you remember those cardioids and limosons and all those kinds of things, probably have something to that effect going on this one, but with 3D. So kind of a dimpled sphere on this one. So anyway, you can experiment with those, do whatever kinds of equations you want to do, type them in, see what they look like. If it ever says it doesn't know what to do with it, you might have to do some restrictions, especially with the cylindrical and the spherical coordinates. But generally, if you have like a rho equals in spherical, it'll do it. Cylindrical, if you have a z equals, typically it'll do those as well. So hope that was helpful, and we'll see you on the next video.